Yeah, then we can start with the topic for today, and the topic for today is three-phase electric power systems. And so, as usual, we will start with some introduction and mainly look at symmetrical three-phase systems, and then you will see there are two different ways to connect them, star and delta connection. So we will take a look at this and probably end somewhere here. And the remaining thing, especially unbalanced system, from my point of view, is for your scope, for your lecture. You can have a look at this. It will be nice and informative, but we will probably not deal with this in the exam because we don't even do this with our usual German electrical engineering students that have 2 semesters for the whole lecture. Because this is real life, but this is also really complicated. Okay, so what did we consider previously? We considered something like single phase systems, right? We always had, for example, a generator, a source. The 230 volts is what? RMS. Is the RMS value of our power mains outlet, Steckdose in German, and the square root of 2 converts it into a peak value. And so we have some sinusoidal harmonic voltage then. Omega is the angular frequency. It's 2 times P times F, the regular frequency, and the regular frequency would be 50 Hertz in this case. And then we have some load, and the load in this case consists of a resistor and some inductor. I would say, okay, this is then some ohmic inductive load. And if we want to calculate the current in this case, how would we calculate the current? If I copy this and paste it into my drawing program, just to do a quick recap, how would we calculate the current here?
V over R. R is R. Yeah.
Yeah. So we would at first convert this into some complex phasor and say our source voltage here. And if we do it as some RMS phasor, we would just use the 230 volts. And if we start with some sinusoidal function without a phase shift, okay, we could add it's multiplied with EJ 0 degree, but okay, this is just 1. So we could also neglect this in our formula here. Okay, so then from the current, from this complex voltage phasor, we can calculate the current. And the current, the complex current phasor would be the voltage phasor divided by complex impedance Z. And the complex impedance Z in this case,
R plus J W L.
exactly, is R plus J omega L. And yeah, so from this we get a complex quantity for the current, some complex phasor. And how would we get back to some time function? Any ideas for this?
We need to have it in the exponential form and then...
Yeah, so we would need to have back magnitude and phase of this. So we would need something like if I write it like this, square root of 2 multiplied with the RMS value, and we started with some sine function, so we will end with some sine function that also depends on omega plus omega times t, and we need to have some phase angle here. And this is the magnitude of this current, or the RMS value. This is the phase. So how do we get the magnitude of this?
Square root of real power squared and imaginary power squared?
Yeah, and so in the simplest way I could write, I just take the magnitude of this complex current phasor. And so at the end, this would be the magnitude of the voltage divided by the magnitude of this impedance. And okay, the magnitude of the voltage we have here, this is our voltage magnitude or RMS value. So I could say this divided by square root of R squared plus omega L squared. And how do I get this phase angle? Yeah, the inverse tangent or arcus tangent of the imaginary part of this current, of the complex current, divided by the real part of this complex current. And then we would need to make sure that this, right, that we are in the right, if the real part would be negative, that it's the right angle. Sometimes we might have to have plus or minus 180 degree. Yeah, if the real part of the current, this is not looking too nice, if the real part of the current would be negative, and yeah, because we have no phase angle here, and we just have the phase angle then of the impedance, but because the impedance is in the denominator of this fraction, so in this case we could say it's the arcus tangens of the imaginary part. Yeah, and so I'm somehow writing into my camera window, so let me write this on the other side. So in our case, what would also fit is the arcus tangens of the imaginary part of the impedance divided by the real part of the impedance. And because of the current is 1 over Z, what do we need to change in this formula here? Because nah, not really. It would be a lucky guess, but just a lucky one in this case. So I mean, here I could say this is current multiplied with the phase of the current. And so here I could also say, no, yeah, and this is what we get from voltage divided by impedance multiplied with the magnitude of the impedance, because I mean we have no phase angle here. The phase angle here is 0. So the phase angle of the current and the phase angle of the impedance what would you say? They are the same, but they are the negative values of each other. So what I need to change here is a minus. And so the imaginary part of the impedance is omega L. The real part is, I would not take this seat. Oh, okay, you can take the chair, but I would not sit there in your case. So we could just write it like this. Yeah, and so now I could say, okay, this is voltage divided by square root of R squared omega L squared, and the phase is minus arcus tangens of omega L divided by R. And so if I add this here for this here in this equation, I won't do this. I could add, or I could insert this term, and for the phase angle here at this position, I could insert this term here. And so then we would have successfully calculated this single phase system. And this is what we have done before. This is what what you should more or less know and be able to do. Okay, so then let's continue, or let's extend this to systems with more phases, so-called polyphase systems. I at first thought that is some strange translation by DeepL or by ChatGPT or so, but it's really the right term. So I've opened up the corresponding Wikipedia pages here, and I'm not sure if it's on this page, but we can, yeah, here, so here it is, yeah. So a three-phase system is a type of a polyphase system having more than 2 or 3 wires. And so this would be the very general case. We have m different interconnected circuits that are all powered by some voltage source and that have the same amplitude, the same frequency, but different phase angles. And so the usual case, the typical case is that we have that m is 3. And so in the general case, the 360-degree, the full rotation is divided by m. And so if we have a 3-phase system, if we divide 360 by 3, what do we get? 120. And so in a 3-phase system, the phase shift between each phase is 120 degree. And usually you take negative. I mean, it's some question of definition, but usually we would say that this phase shift is negative. So this would be some unusual way to represent it, but this was a very compact way. That's why I've chosen this for the slide here. But we have 1, 2, 3 voltage sources. They are connected on one side with each other. Each source is connected with some load. And all the loads are also connected with each other on the other side. And you can see the magnitude is the same. The frequency is the same. This has 0-degree phase shift. This has minus 1 times 120. This has minus 2 times 120, which is 240. And so now the question would be, once again, what are the currents here, for example, in this case, in this circuit? And yeah, we won't calculate it now, but that's more or less the idea of the lecture today. So to give you some equations, some knowledge, how to do calculation in this case. And of course, if we know the current, then we could calculate the voltage here. If we know current and voltage, we could calculate complex power once again, and so on. Yeah, so that's the problem, that's the idea, or that's the question. So where are these 3-phase electric systems used? For electricity generation. So this is one of the few pictures that I found where we have some conventional power plant. I would say this is probably not a nuclear one because there is some chimney. So it's probably a coal-fired one, yeah, but some conventional power plant. The generators in there work with 3-phase current and voltage. Also wind turbines work with 3-phase generators. Now, if someone looks this and really has some knowledge, would you recognize what is the brand, what is the company that produced these wind turbines? It's Enercon. You can the pros can see it because they are painted in green at the bottom of the tower, and they are quite big here on the top. And they are big because they use, I don't know, 20, 27, 30, something. No, it must be something that is divided, can be divided by 3, but they use generators with much more phases than 3. And why? Because then you can use the generators there without transmission system. So the generator rotates really with the same speed as the rotor, and the rotor does not rotate that fast because the tip cannot be faster than the speed of sound, because otherwise they would be very loud and not very efficient. So yeah, the speed of rotation is somehow limited here. And usually if you would just use a three-phase generator, it would also not be very efficient. Anyway, that's why they have this large diameter, because they have much more phases. But in general, wind turbines, what comes out of the wind turbine is a three-phase system. There's some power inverter there, some power converter. And what is fed into the grid is a three-phase system. So then electricity transmission, if you go to my hometown, Wolmirstedt, and there's some big power distribution factory. So there are lots of these towers, and so here you can say there's one three-phase system on one side, and on the other side we have probably this is one three-phase system and this is another three-phase system. And so all these overhead transmission lines also work with three-phase systems. I mean, at this position we could discuss why do we have, and I mean it's all AC, it's all 50 Hertz in Europe and in most parts of the world. In the United States it would be 60 Hertz for historical reasons, and so that all motors will rotate quicker in the United States. Yeah, but why it's AC?
Because it's transformer?
Yeah, because you can transform AC voltages easily up and down. And so if you want to transmit electricity over greater distances, and if we maybe quickly go back to the schematic here, so if we would take a look at the power loss, it's not really related to our previous calculation, but we can without problems add it here. So if we want to calculate the power that is dissipated in this resistor, because every cable that we have here will also act as a resistor, and it will be like some additional resistance, right? This is the wire, this is our power plant, this is our industrial facility, or our households, or a village, or a city. This is our load, and in between we have these overhead transmission wires, and the wire also has some resistance. So if we calculate the power that is dissipated inside this resistance, what formulas could we use? We could use voltage times current, and so we would need to have the voltage drop across this resistance here. And so if we insert that the voltage, how could we calculate the voltage from the current? Just using Ohm's law. So
Current times resistance.
Yeah, current times resistance, and if we take this and insert it there, then we end up with R times current squared. So to lower these transmission losses, we have two ways. We could lower the resistance, and lower the resistance means, okay, we would need to have thicker wires. Not very practical, because then they get very heavy and very expensive. We could use wires with a very good conductivity, so the material with the best conductivity is silver. Okay, would be also very expensive. Even copper is too expensive for overhead wires. So here these are made out of aluminum on the outside, which has quite a good conductivity, right? Something like 60% of copper, and steel in the center, because steel gives mechanical strength, but the conductivity is not that good, and aluminum on the outside has better conductivity and at the same time protects the steel from corrosion and from the outside and so on. And because of skin effect in AC, the current also mainly goes on the surface of this wire. Okay, so lowering the resistance is not really an option, but lowering the current is a good option. And I mean, still we want to transmit power from here to here, and power, as we can see, is voltage times current. So if the current needs to be small, the voltage needs to be high. And that's why these overhead electricity transmission systems works with voltages in the kilovolt range. So in Germany, I think what is usual is 220 kilovolts, 380 kilovolts. There might be systems around the world that even work with voltages up to 1 megavolt. In China, for example, because China is also a large country. I mean, they need to cover large distances. And yeah, still one problem with the AC is that every cable, every wire, every transmission line that you have there has also some small inductance. Even if it's very small, if you have hundreds of kilometers of these overhead transmission lines, they have some considerable inductance, and of course they also have some capacitance against ground. And so yeah, for really, really long systems, then it's more efficient to convert the high voltage AC into high voltage DC and to convert a DC current, a DC voltage. The problem with the DC voltage is, of course, if you have a failure somewhere and if you have a short circuit, the short circuit, let's say, will burn forever. I mean, here you can have the lucky chance that you have zero crossing every 10 milliseconds. So the current naturally goes to zero every 10 milliseconds, and this will also stop some spark over, some flashes, some short circuit that is burning somewhere, and you don't have this with HVDC. So there must be other precautions against short circuits. And you need, of course, to have converter stations, but then it's very efficient to have HVDC. And so in my hometown, Wolmirstedt, there is currently, unfortunately, I missed there was some excursion organized by our student council, and there you could visit this converter station that will be put into operation, I think, at the beginning of this year. To transmit power, because we are in Saxony-Anhalt, we have a flat land and we have lots of wind, so we have many wind turbines, as we can see here, but we have no industry. The industry is somewhere in southern Germany, in Bavaria, in these places, so we need to have HVDC to transmit electrical power and energy, and HVAC to transmit the renewable energy that we produce here to these places. So yeah, also industrial facilities, consumers of high power automation systems, they will use three-phase electric energy. Internally, in most cases, these robots and the drives there also work with, sometimes with DC, also with three-phase AC, but usually because you want to control them, they are not directly connected to the grid. There's also some power electronics, some converters, frequency, variable speed drive systems in between. And but the motors inside there, they will work as three-phase AC drives. And these motors are quite cheap, very robust, and have a good, let's say, power to volume, power to weight ratio. And the advantage against DC drives is that in a DC drive you need, or in a classical conventional DC drive, you need to have a commutator to get the current from the outside to the rotor. And so in these drives you don't need these commutators, and so you don't need brushes, and you don't have arcs at these brushes, and you don't need to replace these brushes every, I don't know, 1,000 hours of operation. So yeah, they are much better and much efficient electrical drives. And probably you will have a lecture about electrical drive systems in the next semester. So you will learn more about these drives. Because yeah, there are also synchronous machines that really rotate with the very same speed as this as our three-phase system, and they are asynchronous machines that rotate, let's say, slightly slower than our three-phase system, because they need this slip, this difference between the outer field. The outer field would always rotate with the same speed as our mains grid, and then in this asynchronous motors there is some field induced in the rotor, and you need to have the slip, you need to have the difference for this induction. And so, yeah, they then will rotate slightly slower, maybe 2% less, 5% less, something like this. But yeah, so this is what we will talk about in other lectures. So this is how such a motor or such a generator would look like. So you have a rotor, and the rotor is a magnet, could be some permanent magnet, but then yeah, you need to have material to give you this permanent magnet. So usually the rotor is also made out of coils, and these coils will generate the magnetic field, but they will create something that we have a north pole and a south pole. And then we have 3 induction coils around this. And these 3 coils are rotated mechanically by an angle of 120 degrees. And so now if we rotate, yeah, if we are in the use this as a generator, we would take some mechanical force, some mechanical power, maybe from some turbine, or from the wind, or from water energy, something that can rotate this rotor. And now we have a magnetic field that is moving within these coils. So what happens?
Induction.
Exactly, induction. We have a changing magnetic field, we have a changing magnetic flux, and there will be some voltages induced in these coils. And if all the coils are made the very same way, then all the 3 voltages will have the same magnitude. And because all the 3 coils also see the same rotating rotor, they will also all have the same frequency of, which is the frequency of rotation. So they will have same magnitude, same frequency, and because of this offset or shift of the coils by 120 degrees in space, let's say, there will be also a time shift, a phase shift of this induced voltages by 120 degrees. And so these will then be the voltages that we could measure at this coil, at this coil, at this coil. And this is what we would call a symmetrical 3-phase system, because if we have a symmetrical generator that we just looked at, and if we have a symmetrical load, so if in our load all the resistors or the inductors, for example, would be the same, so then we have 3 voltages, and as just discussed, they feature the same frequency, they feature the same amplitude, and they would all have a phase shift against each other by 120 degrees. Okay, so now we need some mathematical description, and the mathematical description would look like this, that we say, okay, there is some amplitude of all these voltages, the amplitude is the same everywhere. We have some angular frequency, the angular frequency is the same, it's the same sinusoidal dependence, and the second voltage is once again phase shifted by minus 120 degrees. The third voltage is phase shifted by 200 or minus 240. So yeah, if we plot this, looks like this. And so if we would just plot the first one, right, we get some sinusoidal curve and 360 degree. I think here it would be better to add the degree sign for this phase angle, but after 360 degree it just replicates each other. And so if we have something negative here, some negative phase shift, then it means we delay this function. And so delay here means let's say the peak happens at a later time, or the first positive zero crossing happens at a later time. And yeah, this is more or less the reason why why we have this minus here. As said, it's a matter of definition, and so if this is minus, then it means the phase sequence that we have here is phase 1, phase 2, phase 3. If we would have a plus here and a plus here, then it would be phase 1, phase 3, phase 2, right? Then we would count downwards. So here we count upwards, 1, 2, 3, otherwise we would count downwards. 1, 3, 2, 1, and so on and so on. Yeah, so these 3 voltages are also called phases. It's some additional meaning of the word phase, because this is the phase shift of the second phase. The phase of the phase is minus 120 degrees. Yeah, so this is what we call phase, and this is the 3 voltages is also what we call phases. Can be confusing, but you will see it from the context, I would say, what happens there. Okay, so at this time, I would say it would be a good idea just to check once again what happens here to, for example, also plot this in Octave to get a better idea. So yeah, this is the wrong thing. So okay, this way I can make it smaller. So if we go back maybe to this figure here, so how could I plot the same diagram in Octave that we have just seen? Any ideas? Yeah, so we would need to have these sine functions there. So let's say our amplitude here, as we've discussed, is square root of 2 times 230. What do we get there? Do you recognize or you remember this value? Yeah, something like this, 325, I would guess. So something like 325. This is the peak voltage of our power outlet. This is the RMS voltage. This is the peak voltage. So then we need to have the frequency. Frequency is 50 Hertz. So how can we calculate angular frequency? 2 times P times F. So then we need to have some time range for this. So how can we get a time range? What would be a meaningful time range?
1 over F.
Yeah, 1 over F would be periodic time. So if we calculate 1 over F, and the periodic time for our mains frequency is 20 milliseconds. So we get 20 milliseconds, and then we could say, okay, our time range, we will use something that is linearly spaced between 0 and maybe 1.5 times the periodic time, like in the plot before, and let's take, I don't know, 301 points. And I will escape the output. Okay, yeah, because now our time here is 301 points. Okay, so then we should be able to calculate Vs1 is this peak value multiplied with sine of omega times t, and that's it. So for the second voltage, we need to have this phase shift. What do I need to add? Yeah, conversion between degree and radians. So how to convert this degree into radians? Yeah, so we need to divide by 180 and multiply with P. So we get the second voltage, and if I do this once again for the third voltage, with minus 240, then we also have the third voltage. And so now if I plot with respect of time just the first voltage maybe, so takes some time, obviously, because the computer is not the fastest. But there's our first voltage. And don't ask me why, but these numbers in Octave, they are always super small. And we have 1.5 periods, because we plotted it to 1.5 periods of time. And now our axis here is not scaled in an angle like here, but really as a function of time, because I've plotted it as a function of time. So I could also, if I would like to have the same scaling here, I could of course also take omega times t. This would be in radians. So if I take this, multiply with 180, divide by p, then I should get it in degrees. So we can check. Oops, and this does not work. Why does it not work? Because I think maybe now strange things happen. Okay. I think Octave is confused. I will just copy this if my computer allows me to do so. Okay, now this worked. I don't know what was the syntax error here, because usually this should work. Yeah, and so now we have the same, but just in degree. Okay, so yeah, I could add some. I should, if I'm a real engineer, I should add some axis labels, but we will just keep it like this. And so I will say hold on, then I can plot the other ones. So there's the second one, right? There we get the phase shift as before. And this is the third one, which is in this light yellow or orange curve here. So, okay, we will probably need them later on. We have just reproduced this plot, this diagram in Octave, and check that this is really this phase sequence of these voltages. Okay, so then, as we have done before in our single phase example, we can just rewrite them in the complex form. So in the complex form, they also get some magnitude for this complex phasor, and we write the phase as e to j omega. And yeah, so here it would be better, to be honest, to cut this omega t. This would be the rotating phasor, and we just want to have usual complex phasors. So I would cut the omega t here. Yeah, and then we can convert them into RMS phasors. So we just take this peak magnitude, divide by square root of 2, and then we get RMS values. And so this is very handy. We have the same RMS value everywhere, and 0 degree, minus 120 degree, minus 240 degree of phase shift. And this would be useful, meaningful RMS phasors to do calculation here in this case. And so these phasors we can also plot into some phasor diagram. And we can see they all have the same magnitude, and this has 0 phase, this has the minus 120, this has the 240 degree of phase shift. What we could maybe also discuss is how can we generate a phasor diagram like this in Octave? Any ideas for this?
We have to convert them to Cartesian form?
Yeah, so at first we would need to write them as complex phasors. So here is somewhere my first source voltage. And now if I would say this should be complex, then I would just say this just gets the value of my magnitude that I've chosen. So here I should get the 300 or yeah, so yeah, the 325. We had no separate variable for the RMS value. Okay, so if I do this for the second one, multiply with some exponential function minus j multiplied with 120. Once again, I need to convert from degree into radians. So this should be a multiplication here. And so the output then, what Octave will display for us will be the real part and imaginary part. And we can check, okay, the real part is negative, the imaginary part is also negative, is slightly larger or is considerably larger. And so if we do the same and just for the third voltage, then we need to have here the minus 240 degree of phase shift. And as we can see, we get the very same real part and the same imaginary part, but just negative or positive or whatever you would say. Okay, and so to plot this in Octave, there's a nice function that is called quiver, I think, which is something like arrow, drawing an arrow. Does anyone who knows English and German knows what quiver means?
Zitter.
Oh, okay, interesting. And so this quiver plot works in a way that you give, let's say, x and y values of the start and x and y values of the end of the length. So if we start to check it out, so if we want to draw the first one, which starts at 0 and 0, and this ends at, as we just said, the real part of this and the imaginary part of this. So I need to have another closing parenthesis, and there should be our, okay, we still have hold on, which is not a good idea in this case. So
should they both be the same number?
And they should have the same number, of course. Talking and writing sometimes is difficult. Yeah, and this now also makes sense. We have some horizontal phasor pointing in this direction. And so now I can do the same trick, say hold on, plot the second one. I don't think that it will get a different color in this case. Oh, it gets a different color, okay. So there's the second one pointing downwards. And if we just repeat this for the last one, then this should point to the upper left corner, and it does. And so by comparing the two, still looks a bit strange. Why does it look a bit strange? It looks a little bit distorted, right? I mean, here the angles are nicely 120 degree. And here, this looks larger, this looks smaller. This almost looks like 90 degrees, some right angle. So what could be the reason for this?
Scales.
Yeah, the scaling of the axis. So if we here say axis equal, both axes should be equally scaled, then this looks much nicer and much better. So this quiver plot would be some way to plot such phasor diagrams in Octave and MATLAB if you ever need to. Okay, so what we can now do with these phasors is we can calculate the sum of these three sinusoidal voltages. So first voltage, second voltage, third voltage. If we would like to calculate the sum as a formula like this, it's really complicated. Of course, we can do it in MATLAB, no problem, right? Remember, there was my plot function here, and I need to say hold off. There was my plot function that plotted, for example, the first sinusoidal voltage, which looked like this. And yeah, so I could of course also plot all the three into one joint diagram. So to say, okay, once again, as a function of time, we want to have a second voltage. As a function of time, we want to have the third voltage. So once again, I should get all the three voltages in one diagram. And so now, of course, what I can do here without problems, because it's not really a formula anymore. I've converted the formula just into a bunch of values, just some array of values. So here, without problems, I can do this first voltage plus second voltage plus third voltage. So before I enter, so now we take this function and always add the red and the yellow function. So we just calculate the sum of these three functions. What should happen?
Oh, 0?
Okay, we can check. So here we have something 0, here we get something positive, here we get something negative. Should be 0, okay. Here we get something positive, you get 2 times something negative, but what is half the size? Okay, looks like 0. So here we have the same, something largely negative, something that is half the size positive, but 2, we should get 0. So we should get 0. Let's try it out. And so we really get 0, which, yeah, perfectly makes sense. And so it's of course easier to do this calculation in a complex domain. So if we take these 3 complex phasors and just add them up, convert this complex form or exponential form, polar form, into Cartesian form, right, with cosine and sine, and think about what is the cosine of minus 120 degree and so on, then we also end up with 0. And this is also something that we could, yeah, more or less see from this phasor diagram. So if we take the first phasor, which was pointing in this direction, then add the second phasor, which was pointing in this direction, add the third phasor, which was pointing in this direction, then we end at the same point where we started. And so the sum of these 3 sinusoidal voltages is 0, and this is really some important essential feature characteristic of these symmetrical 3-phase systems. This is yeah, really the usual abbreviation for 3-phase systems that was also not invented by ChatGPT, but that is Wikipedia knowledge. And so once we are at this Wikipedia page, I think, yeah, so you can see the same phase diagram, phase order here, 3-phase AC transmission and transformers, and there was somewhere, yeah, so there's a nice but probably at the end not super helpful animation of how these currents look like. And I think the nicer animation, what we also just discussed for the generator or for the motor, is this one here. So we have these 3 coils and we have the rotor with the DC North Pole, South Pole magnetic field in the center, and then you can see how these, yeah, how the voltage in each of these 3 phases looks like. And the sum of these arrows would be really one joint rotating phasor that is yeah, rotating like the motor, which is also very useful for these AC drives, and the reason why they work like this, or why they are working that well. And this calculation that we have just done here, as we have our 3 complex phasors in Octave, we can of course also just try out in Octave. So the first complex phasor looked like this. Yeah, so we have real part of 1, no imaginary part. The second complex phasor looked like this. So half of this negative as the real part, some other value. Does anyone recognize what is this value here? Or what is the sine of minus 120 degree? Who has a good mathematical view? Yeah, it's square root of 3 divided by 2. This is this value. And so for the third complex phasor, right, we have this. And so also if I take the sum here, so the first one complex plus the second one complex plus the third one, I should have used some copy and paste. Complex, but at least the tab is working. So yeah, okay, interesting effect once again. We don't get 0 exactly, but we get something very, very small. And interestingly, it's somehow larger. With EPS, you can get the internal precision of Octave, and the internal precision is something like 2 times 10 to the power of minus 16. Okay, but this is reference to 1, and so our values are a little larger. So I think if we take this EPS and multiply it with our magnitude, yeah, so then we get something in this order of 10 to the power of minus 14. And so this value is at least smaller. This is not really smaller, but numerically this is still something like 0 in this case. Yeah, so this makes sense. This is these are, let's say, just rounding errors of the computer. Okay. So the sum of these 3 voltages is always 0. And this allows us to not have only a star connection of these 3 voltages, but to also connect them in a delta connection. And so even if we take the 3 coils of the generator, and if we connect them in a delta connection, because the sum of these 3 currents is 0, there will be no current going in this loop, because there is no source for this current in this loop. And this is super handy, because we could take the very same generator and connect the very same generator in 2 different ways, in the star connection and in this delta connection. And so in the same way, we can also take any 3-phase load, so 3 resistors, for example, if we just have a 3-phase ohmic load, and connect the 3 resistors in the star connection, connect the 3 resistors in the delta connection. And so we have many options to combine star with star, star with delta, delta with star, delta with delta. And they have all their, I would not say advantages and disadvantages, but you just get different voltage levels, different current, different power levels with these different circuits. And so, of course, the assumption for this is that they are equal enough that there's no current induced here, and that these internal impedances are negligible compared to the load impedance. So of course, if the load impedance also gets very small, then strange things might happen. And yeah, so one advantage, because of this connection, this relationship of these 3 voltages, is that we only need 3 wires, or here in this case we might need 4 wires, but we only need, if I really go back to the beginning of my slides, so here we transmit a certain amount of power, and we need to have 2 wires, a forward conductor and a return conductor. And of course, now you might say, okay, a 3-phase system is just, we take 3 single-phase systems and combine them with each other, but then we would need to have 6 wires in total to distribute 3 times the amount of power. And the advantage of this interlinking, this connection here of these voltages, I've not really found. So in German we say Verkettung. I don't really found a meaningful English translation for this, but all the mathematical properties that we just discussed, that the sum here is 0, yeah, so this helps us at the end that we can transmit 3 times the power of the single phase system by just adding a third wire. That's a huge advantage for power transmission, for energy transmission. And so here we need to have a 4th wire, but if this is all symmetrical, then the current on this neutral conductor will also be 0. So we can also remove this wire, or we can, if we really want to transmit power, this would be a thick wire, this would be a thick wire, this would be a thick wire, but this could also be a quite thin wire because there's no real current on this. Okay, so important thing, star connection, delta connection. And there might be different ways to represent them. So don't be confused if you see different representations of this. So let me once again go back in my slides, some slides. So, right, we discussed the 3-phase system here. So what type of connection is this here? Yeah, it looks like a parallel connection. Yeah, so but this is the star because this would be the star point. I could write this to the top and let's say this to the lower right and this to the lower left, and then you can clearly see the star configuration. And so sometimes this delta connection, right here we had the delta connection. Sometimes the delta connection is also drawn like this, that you have, I will draw it for voltage sources. So the delta also sometimes looks like this. You have the first voltage source, you have the second voltage source, and you have the third voltage source. And if we would connect them here, we would have the star once again. And so if we connect this to this side, this to this side, and if we somehow connect this to this side, then we have a delta. Even if not does look too much like a delta, but it's a delta connection. And so this would be the first line, this would be the second line, this would be the third line. So if you ever see something like this, this is also some delta connection in this case. Okay. So we save wires, we save conductors. And so, yeah, now we need to introduce or clear some names, make some definitions. So we have a 3-phase generator, we have a 3-phase load, and one part of this load is what we will call a phase. I think there might be a slide set where this is called a string, but I think this is not a usual translation of this. In German it's Strang, but you might translate this into string for other meanings in a different context. For example, if you have a PV, a photovoltaic power generation unit on your roof, for example, each PV cell only has a quite small voltage. So you need to put lots of PV cells in series to get a meaningful voltage. And so then all these PV cells in series, they would be called a string. And there's also a string voltage across this string, across this series connection of PV cells. So if you Google for string voltage, there will be many hits for string voltage, but it's not related to 3-phase AC. So let's call this a phase. So this would be one phase, this would be a second phase, this would be a third phase of our system. So then we have lines, and these are the conductors from the generator to the load. So this would be one line, this would be another line, this would be another line, and we just call them L1, L2, L3. So then in a star circuit, we can also have a neutral conductor. And the neutral conductor might be also often referred as ground. And this ground for example, here at the generator, the neutral or the ground might be also sometimes connected to the earth, might be grounded. Still, there is a difference between ground and earth. I mean, at the end, they will have a similar potential, because if you put the ground on earth, it will be the same potential. But on the neutral conductor, on the ground conductor, there will be current also in normal operating conditions. Usually you don't want to have a current going over the earth. So a current over the earth always means that something failed in the circuit. Because a fuse has blown, because a live wire touched the ground, touched the earth, something like this. So a current on an earth conductor should be only in case of failure, if something more or less terrible happened to your circuit. That's the difference between ground and earth. So ground, current on the ground, no problem. Current on the earth, typically a sign of a failure. Okay, so then we have line-to-line voltages. So line-to-line voltage would mean we have a voltage from one line to the next line, a voltage from this line to this line, a voltage from this line to this line, which also makes sense here. And we might have in the star connection line to ground voltages, so voltages from line to the neutral conductor. And then we can have phase voltages. So this would be a phase voltage because it's the voltage across one phase. This is a phase voltage because it's a voltage across some phase. And we can also have, in the same way, line and phase currents. A line current is a current on the line. A line current is a current on the line. A phase current is a current in the phase. A phase current is the current in the phase. And so now if you think about this for a moment, wait. Here, in the star connection, the phase current is the same as the line current, right? And this is not the case here. Here the line current is different than the phase current. But the line-to-line voltage here is the same as the phase voltage here. But the line-to-line voltage is not the same as the phase voltage here. But the line to ground voltage is the same as the phase voltage here. And so, yeah, this is some important property. I think there will be several slides devoted to explaining this, but at the end I think it's not too easy to, not too complicated to understand, right? So in the star connection, phase current and line current are equal. In the delta connection, phase voltage and line voltage are equal. And in this star connection, line to ground voltages and phase voltages are also equal. Okay, and so these are all the names that are explained here. And once again, there might be some slides where this is called string. From my point of view, it's not the optimum translation in this case, because it can be super confusing. Okay, so now let's do something that helps us in writing down mathematical formulas. And you have seen that we always have this e to j minus 120 degree. And now we take, and yeah, from my point of view, this is kind of a also not optimum definition, but it's the usual one. Now it's difficult to change it. We are in some lock-in effect. There's no minus here. It's just a positive 120 degree thing. But let's call this A. And it's called rotation operator. It's a complex number. It just does rotation. Rotation by 120 degree. So yeah, what we can calculate from our phase operator there. So I will try to move my Octave window here a little bit to this side. So, and say A is e 2j times 120 degree, and once again we need to divide by 180 multiply with p. And so if I calculate this, we get real and imaginary part, and we should get we get numbers that we have seen before, because we get 0.5 and so 1 over 2 and square root of 3 divided by 2. Okay, so this is this phase rotation operator as real and imaginary part. So what should be the magnitude of this? What should be the magnitude of this complex exponential function? The square root of the 2, okay. Who's good in doing this calculation in the head? But if you just look at the brief definition, what should be the magnitude of this? Yeah, it should just be 1. It's just a rotating phasor in a unit circle. So, okay, if we take the magnitude of this, it's 1 by definition. Okay, so what else can we do? What is the phase of this? 120 degree. So what is the reciprocal value? So 1 over a. What would be 1 over a? If we calculate 1 over this exponential function, if you divide by a power, it's the same power but with a negative exponent. So if we take 1 over a, negative exponent means we should get the same real part but the negative imaginary part. We get the same real part, negative imaginary part. And negative exponent also means complex conjugate. So if I take the conjugate of a, it's the same thing. Okay, so then what would be also interesting is what happens if we take the square of this. Yeah, we should get if you take the power. No, yeah, if we take the power of a power, we multiply the exponents, so we should get 2 times 230. So if I take a squared, okay, we get something like this. This is, we can check, it's really the same as 230 divided by 180 and p. And it's the same as, so it's the same as we had before, right? It's the same as 1 over a, it's the same as the complex conjugate of a. So a squared is the same as a minus a to the power of minus 1. Okay, and so if we take higher powers, if I would take a to the power of 3, what would you expect then? Three times 120 is 360, so we should get 1. We should go to the point where we started and we get 1. We don't get exactly 1, right? We once again have this very small thing that is inside the range of the accuracy of our computer here. Okay, and so a to the power of 4 should be the same as a again, and this also makes sense. Okay, so with this rotation operator, we can rewrite our 3 voltages just using the first voltage. And so we have 1 here, we have a squared here, because a squared gives the minus 120, and this gives the plus 120 or minus 240 degree phase shift. Okay, and so with this, for example, we could once again calculate the sum as we did before. We can check, I mean, if I take 1 plus a to the power of 2, we get 0 or something close to 0. Okay, so now using this we can write down differences of the voltages using this rotation operator. So for example, I could calculate from our phase voltages, these are the phase voltages, or these are the line to ground voltages in the star system. I can calculate the line to line voltages, because this would just be a mesh equation. And yeah, so I get something like a minus 1, or a squared minus a, or 1 minus a squared. So the question is how to calculate these voltages then. And yeah, so here's the long way. We can just go back to Octave and check one of those. So for example, if we do a minus 1, right, we get something like this here. I think here something went wrong here. I think there's some equality sign missing. But we can check the magnitude of this by taking the absolute value. And the magnitude, we get this. Does this look familiar? What is it? Square root of 3. So if we take square root of 3, we get the same value. And if I take the angle of this will be in radians. If I multiply with 180 divided by p, we get 150. And so this is at least what is correct on the slide set here. Square root of 3 multiplied by e to j 150 degree. So if we would do it for the next voltage, which is a squared minus a, so we get minus 90, and we get the same magnitude, also square root of 3. And so for the last one, we also get square root of 3, and we get a different phase angle, which is once again, so here we start with something, then we have minus 120, and we have another minus 120, which somehow makes sense. Or is this no? I think from here to here, no, it's plus 120, right? From here to here we get to 270, and then this is the same as minus 90. And so from here to here we have plus 120 degree. Okay, so long story short, these are the phasors that we had before, remember? And so we can write the phasors of our voltage using this rotation operator. And we can also write the differences of these rotation operators by the rotation operator. And so we get a new, so this is a symmetric three-phase system, and we get a new symmetric three-phase system. And so the same phasors I've just written here in a different way, but I think I think they should have pointed inwards. Something with the direction here is wrong. Yeah, so a minus 1, so if we go into the direction of a and do a and minus 1, I think these here are wrong. This should point upwards, and this should point downwards, and this should point upwards. Right? Otherwise it does not make sense. And then it would also fit to what is written here. So I probably need to correct this in the slide set here. But you get the idea. So we have our original system, we do differences, and we get a new three-phase system. Okay, and this new three-phase system has the same properties as before. They all have the same magnitude. They would all have the same frequency, and they are once again phase shifted by 120 degree, or by minus 120 degree, question in which direction you rotate. Okay, so now with this we can once again take a look at star and delta connections. I think this is more or less what I've explained already. Yeah, so here in the star, phase voltages are the same as the line to neutral voltages, and phase currents are the same as line currents. So we can rewrite them using our rotation operator here, and so then we can calculate line-to-line voltages, and from our rotation operator and from what we just did here, yeah, we get this factor, of square root of 3. So the line-to-line voltages in the star connection are square root of 3 times larger than the phase voltages. Okay, and so from the 230 volts multiplied with square root of 3, we get to 400 volts. And 400 volts is then the other voltage level that you get in a three-phase AC system. And this is another advantage of three-phase systems. We have two different voltage levels. So if you have, I think unfortunately I don't have something here, but if you have a power outlet for a three-phase system, depending on how you connect wires there, you can get 230 volts of RMS, or you can get 400 volts of RMS from the same power outlet. This is also some important advantage of these three-phase AC systems. Okay, now in a star system, line current is the same as these phase currents. What we discussed before, just written down here to make sure that it's written down. Okay, so then if we use our rotation operator, okay, and this is what we will also do in the exercise, right? That's why I'm going over this a little quicker. If we calculate the current on a neutral conductor, we once again see the sum of our phase operators here, rotation operators, current on a neutral conductor will be 0 if everything is symmetric. So the neutral conductor does not carry any current. We could also remove it. If we really have a symmetrical system, it would not change anything at the system. Okay, so then we can have a look on the star, on the delta circuit. So as discussed before, in the delta circuit, these phase voltages are the same as the line-to-line voltages, but the line currents are not the same as these phase currents. And it always looks like that two phase currents form one line current. Or that one line current somehow splits up into two phase currents here. So if we just take a look quickly at the voltages, as discussed, the voltages are equal. Yeah, and so now if we check the currents and would say, okay, in each phase of our conductor, we have the same current, just rotated by our rotation operator. And now we use a Kirchhoff's current law and write down, for example, at this position, a Kirchhoff's current law. That would tell us this current, in this case, for example, this current minus this current should be the same as this current. Right? So first current minus the third current should be this first line current. And this is what we just calculated before, 1 minus a and a squared minus 1 and a minus a squared and so on. And what was the result of this? Yeah, square root of 3. So it's once again a three-phase system, but it's square root of 3 times larger. So in the delta connection, the line current is square root of 3 times larger than the phase current. very short written in this way. And so if you change the current into voltage, this was the equation that we had for the star circuit. And if you here change voltage into current and voltage into current, then this would be also the same equation for the star circuit. And so remember, we maybe discussed this idea of duality, so that we have circuits that behave the same if we exchange current and voltage. And so the star circuit and the delta circuit are somehow dual circuits, similar circuits. They behave similar in a way that we have the same equations, but we would need to interchange current and voltage. I would say the important thing is remember this factor of 3. Yeah, and remember that, okay, so if I go back to the star circuit, here current and current is equal, but voltage here and voltage here is not equal, or phase voltage, line voltage is not equal. The line voltage is 3 times larger. And so here voltage and voltage is equal, but current is not equal. The line current is square root of 3 times larger. This is what I would remember. This is what I can remember. And I don't have that big brain to remember stuff. So this is what I can do. Probably you can also do it. So then we could do the same thing at the load, and at the load, of course, same things will happen, right? So I mean, here we have some line current. It will be the same phase current here. We have line to ground voltages will be the same as the phase voltages here, but we have the line to line voltages are not similar. So also line to line voltages will be 3 times larger than these voltages here. So these voltages will be square root of 3 times, excuse me, square root of 3 times smaller than these voltages. And we can derive this using our rotation operator and yeah, do this and find out, okay, line voltages are square root of 3 times greater, or phase voltages are square root of 3 times smaller. And the same is what we can do for the delta connection. And so here once again, right, the voltages are equal. This current is square root of 3 times larger than this current, so this current is square root of 3 times smaller than this current. And you can write it down by equations, end up with this factor of 3 with the same calculations that we done before. Yeah, so I mean, I think this is a nice slide set to take a look and learn this yourself. It's not a very nice slide set from my point of view to doing these explanations, because there's lots of redundancy in these slides. But okay, I've not, at least not this part created by myself. So to summarize, and I would say this is the important thing to remember. This is one of the take-home messages. In the star, as said, currents are equal. In the delta, the voltages are equal. Here, the line voltages are 3 times larger than the phase voltages, and here we have the same relation for the currents. And this square root of 3 factor is super typical for these systems. So you will find it each and everywhere. Okay, so now the last thing that we will do for today, and as said, I would say the last 3 chapters, if you want to take a look at this, take a look at this. I think it will not be very relevant for the exam. Still maybe nice to know and interesting to know. Now we connect sources and loads with each other. So these are, as said, the 4 options that we have. We can have delta and delta, star and star. I would say this is the most common one probably. We can have a star source and a delta load, or we could have a delta generator or source and a star load. And if everything is symmetrical, which is nice, then in all phases in all three phases happens the same. They are just shifted by 120 degrees. So it's sufficient to calculate one phase, and if you know what happens in one phase, in the other three phases it will be the same, but just shifted. Okay, so if we do this star-star thing, voltages are equal, currents are equal, and we can just calculate current by Ohm's law. Nothing really interesting happens from my point of view, and the line voltages, as discussed before, are square root of 3 times larger. Okay, so if we do a delta-delta connection, it's also quite simple because voltage here will be the same as voltage here. If this is symmetric and this is symmetric, then also the current here will be the same current as here because of this symmetry. So if we want to know the current, we just use Ohm's law to calculate them. And here the current on the line is, as discussed before, 3 times larger than the current in the phase. Okay, so yeah, these were the two, let's say, easier things. Now we can do something slightly more complicated and say, okay, we have a star source in a delta load. And so we have some voltage here. Let's call this Vs in the phases of our source. So this is the reference. This is, let's say, the 230 volts. So from 230 volts as phase voltage, we can calculate the line-to-line voltage, which will be square root of 3 times larger. So this would be 400 volts. So the 400 volts is what our loads will see here. So now we can calculate the current here, and the current will be the phase voltage, which is 3 times of the phase voltage here divided by our impedance. Once again, Ohm's law. Okay, so then we get the phase current here, and the line current is once again square root of 3 times larger. So square root of 3 multiplied with another square root of 3 will be 3. So the current, so this S here now stands for source. The current in one phase of the source will be 3 times the voltage of the source divided by the impedance. And the 3 comes from 1 square root of 3 and another square root of 3. But still nothing really complicated, just square root of 3. And okay, maybe we will skip this derivation because it's just that with the symmetry and so on. So let's come to the next or to the last point. We have a delta here, we have a star here. We do the same thing. Now at the end we have 1 over 3 because we have like 1 over square root of 3, another 1 over square root of 3, and we divide by 3. That's more or less it. And so now if you imagine that we can, for example, have the very same source, and one time connect a load like this, and one time can connect a load like this. So one time we get in the load or on the lines, we get square root of 3 times more current. And if we calculate power, for example, using this equation that we've written down, power is proportional to the square of the current. So if we have square root of 3 times more current, we get 3 times more power. And this is then also some advantage of 3-phase systems. So I have a load, I have a source, and I have, for example, 3 resistors as a load to have a heater. If I connect the 3 resistors like this, I get a certain power. If I take the very same three resistors and connect them like this, I get 3 times more power. If I take the same source and now also connect the source in this way, I get at the end 3 times more current, and so I get 9 times more power. So I can, yeah, you can play around with powers. And so this of course also works the other way around. So we could, for example, also have a motor and connect a motor. Have you learned something like this in your vocational training, changing of motors?
I'm not sure.
Yeah, so to limit the inrush current of motors, you have a big and powerful motor and you directly connect it to the grid. And the motor at the beginning needs to start to turn, and so there's no counter voltage induced in the motor, so the motor will draw a very large current from the mains grid. And this will lower the voltage, and it might trigger the fuse and so on. And so this is also one option. We start with the motor in this connection, and then we switch to the delta. Yeah. So if you have a large powerful motor, you would do it the same way. Start the motor in this configuration. Then the motor is not that powerful, but it will start to turn, and but it will not use so much inrush current. And once the motor starts to rotate and the current goes down, then you rapidly switch the motor to this configuration to go to full power, but to limit the inrush current at the beginning. And so this is also what is done with motors. But if you have modern drive systems with power electronics, variable speed drives, they all do it internally. Yeah, but this is also some advantage. You can get different powers of these 3-phase systems. And I know we are a little bit over time already, but if we, one last thing that we might try if we are here in our Octave window, and if we already had the plot here and discuss that the sum of the 3 voltages is 0. So something else that we can discuss related to power. And so we could also write this equation here as voltage squared divided by resistance. And I think this is some other cool property that we can discuss really as the last thing for today. If I go back to my plot command here, and so if I take the first voltage and square it, if I take the second voltage and square it, if I take the third voltage and square it, and maybe cut the remaining thing here. So these are the same voltages squared. If you square some sinusoidal function, you get another sinusoidal function. And so now if we take the sum of these 3 powers, so the power in the first phase, right? The power that we have here plus the power that we have here plus the power that we have there. So with respect to time, I will now take this so plus the second voltage squared plus the third voltage squared. And I think I need to enlarge this window to check if I have everything correct, but it looks good. So this was the plot that we had before. Now what would you expect if I take the sum of this, the sum of this, the sum of this? Yeah, they are not symmetrical, or they are not around 0 anymore. They are always positive now. So it's not that negative and positive values can compensate with each other. But as what we have done before, we could take a lucky guess that we get something constant. And this is really what happens here. So the total power in some symmetrical three-phase system is really constant over time. Yeah, and this is, I think, super cool if you remember, if we go back to this. So we have this rotor in the center, we have 3 coils, and in each coil there's a sinusoidal current. And in each coil, let's say we have a power that changes over time, but if we look at the total power, the sum of everything what happens here in our system, the total power is constant over time. Super cool feature, because this means that the motor runs with the same speed, the same torque all the time. And it's not going faster and going slower and going faster and going slower and vibrating and doing stuff like this is what would happen if you just have a 2-phase motor. The 3-phase motor always has the same torque, the same speed. A 3-phase heater has the same power over time. Instantaneous power is constant. Okay, this super cool feature should finish our lecture for today. Yeah, now we could go to resources, we could look at powers, what we have done very quickly, and then yeah, in practice, these 3-phase systems might not be super symmetrically or super symmetrical. There might be unsymmetrical loads, unsymmetrical generators, and then we would have unbalanced systems. And then I can tell you, it's really getting complicated from a mathematical point of view to take a look at this, and that's why we won't do it. Okay, thank you.